Okay, so welcome to the last lecture of this course. So we are in lecture 15. We continue to look at the paradigm of reinforcement learning, and last lecture we've discussed one main paradigm of reinforcement learning, namely Monte Carlo methods. But we're going to see some potential problems with Monte Carlo method. So let's review what is reinforcement learning. It's a learning paradigm that is aiming to capture how an agent will improve its performance in completing a task through interaction with the environment. The goal is that the agent would want to complete certain tasks, but then the task's performance can only be known after the agent has performed the task and the environment has provided the agent with certain critics that could be either in the form of rewards or punishment. And the task typically is not just a single one-off action, but rather a sequence of actions. So the agent would perform a sequence of actions and get the accumulated payoff from the environment, and then using these payoffs to update its evaluation about its actions. And then using these evaluations, the agent is able to improve its performance, its actions, and therefore improving the performance of completing the task. So that's the paradigm of reinforcement learning, and we see that the action may affect not just the current situation, but subsequent moves, right? Now let's consider a situation, and potentially this will be a situation where reinforcement learning can be helpful. So imagine the situation where you are driving from your home to the university, right? And suppose you leave at 6 p.m. in the afternoon and expect to get home at 6:30. So this expectation is your believed time that travels from the university to your home, and this can be obtained from past experience. But you know, it's through the process of going back home. Suppose you're starting from your office, then you'll walk to the car park for 5 minutes. And when you arrive at the car park, then it started to rain. And then you adjust your expectation. So instead of hoping to arrive home at 6:30, now you re-estimate your travel time, and then you say, well, maybe I'll take 10 minutes longer to get home because of it's raining. So you expect to arrive home at 6:40. So then you get onto the motorway, and suppose surprisingly the motorway is actually not bad. So you only spend 15 minutes on the motorway, and then you would cut your expectation and think that, well, actually it's not as bad as I thought, so I may arrive home at 6:35. Right? But then, unfortunately, after you get off your motorway, then there's a heavy traffic on the road that lead to your home. So you're basically stuck behind some big truck. And this may worsen your expectation. And so you estimate and hope to reach home at 6:40. Then when you finally get onto the street where your home is located at, it's already 6:40, but then it's pretty smooth run, so you expect to reach home at 6:45, and eventually you get there at 6:45. So you can see that this is a everyday scenario that we may face as we're performing a certain task. Every step of the way, we will make certain expectations, and because of the changing situation that we observe, we will update our expectation on the fly, right? So that's, a typical sort of situation, how human would update our evaluation towards our actions. And so we went through, different stages, starting from work. We reach at the car park, and then we get on the motorway. We exit the motorway, and then we find ourselves behind a big truck. But after a while, we eventually reach the street where the home is located, and then we eventually arrive at the destination. So if we apply Monte Carlo, then if you think about Monte Carlo algorithm, what it does is it reevaluates only after we finish an episode. So the entire run from work to home will be treated as a single episode, because that sort of is starting from the beginning of the task and until we finish the task. Only then we get, the accumulated payoff for the entire episode, and then we reevaluate at each of the intermediate steps. But this is sort of counterintuitive, because we as human, we are not reevaluating only after we arrive at home. We're actually reevaluating the travel time as we are driving. Right? So essentially, the Monte Carlo method cannot capture this sort of dynamic online reevaluation process that we as humans made. Right? And therefore, if we really want to think, come up with a natural reinforcement learning algorithm, the Monte Carlo method, obviously, there's something lacking, right? There's still a gap between how a Monte Carlo algorithm learns and how human learns, right? So, in fact, we will need, if we want to simulate how human perform, we will need a learning method that allows the agent to reevaluate at every step dynamically during an episode. So this is before the episode have actually finished, right? So how do we do that? So if we haven't finished the episode, then we do not know the eventual outcome, right? Because, for example, when we just get off the motorway, we hope that, we could arrive home pretty fast. Then, the sort of expectation that we made at that time does not really reflect what happened afterwards, because we have no way to predict how the episode will go after this time instance. So essentially, this requires some sort of bootstrapping, right? Because we haven't really got the outcome of the episode, and then we need to update our evaluation using the current experience, so without getting this final outcome. And this is essentially bootstrapping. And if we recall an earlier lecture where we actually used bootstrapping in the evaluation of a Markov decision process, namely we used dynamic programming to perform the job. And in fact, here we're actually essentially wanted to do something very similar. So we're using these two diagrams to illustrate the difference between Monte Carlo method and the one that we want to achieve. The Monte Carlo method is like this. So we're starting. So this diagram illustrates the changes to our expected travel time as we progress, starting from work to get home, right? So each step of the way, you can see that essentially if we apply Monte Carlo method, we can only do such adjustment after we have completed the entire episode. And once this is completed, we can get the actual outcome of this entire episode. And then with each of the intermediate step that we have gone through, we will update the evaluation according to the eventual outcome of the episode. Right? So essentially, all of these will be adjusted upwards, because eventually the outcome, it's longer. It's much longer than what we have predicted at each step. Right? So that's the Monte Carlo method. But actually, what we wanted was that we want to adjust our evaluation before we receive the final outcome, before we actually finish the episode. So, for example, initially we start at 30. By the time we go to the next step, we change our evaluation to 40. So this means that there already we can update our expectation, our estimation to the first step. To, instead of 30, we are updating it to be longer than 30 minutes. But then after we get off the motorway, we find out, okay, the motorway is actually not that bad. So we cut our estimation from 40 to 35. So consequently, this would allow us to, adjust the evaluation at the previous step and saying, oh, actually, maybe it should be better than 40. So we bring down this evaluation. And then in the next few steps, we just dynamically update according to the next step outcome. Right? So that's eventually, what we wanted to achieve. And this paradigm of learning, which is different from Monte Carlo, we call it temporal difference learning. So eventually, temporal difference learning will combine the idea of Monte Carlo method. The reason is that we are still working with a model-free case. We do not have an explicit representation of the transition function and reward function of the underlying MDP, right? And this means that we need to take sampled episodes. However, on the other hand, we do not want to wait for the episode to finish before updating our evaluation. So this requires a bootstrapping mechanism similar to dynamic programming. So essentially, this temporal difference learning paradigm combines the techniques from both the Monte Carlo methods and the dynamic programming. Just like the Monte Carlo methods, TD learns from experience, from sampled episodes without knowing the state transition and reward functions. But also, just like DP, temporal difference updates estimates based on other learned estimates, such as using these bootstrapping methods. How do we actually achieve that? So now let's think of a run. So this will be suppose that would be an episode starting from S0 to ST. And then for every small case t, which is a value that's between 0 and capital T, we look at a segment of this run. We look at a segment of this episode. This would be the sort of the suffix of the episode, starting from the T step all the way to the very end, the capital T's time. So we look at that part of this run, and then we use capital letter G, T with a superscript pi to denote the expected return, the actual return of this part of the run for the player if the player follows the strategy pi. Right. So we got actually this particular episode, and that will be the return. And then actually, if you think about the Q value that we used in Monte Carlo method, we were approximating the expectation of the return of to the player for a given state and a given action. Right. So actually, what we wanted was to evaluate the expected return. So the expectation of the value of G pi T, where the T's state of the episode starts at S, and the action that the agent has performed is A. Right? So this is the expectation that we want to evaluate as the value of QSA. Right? So this is actually the goal for the Monte Carlo method. And but if you think about these G pi T, it is actually a sum, because that's it's not just a immediate payoff, but it's actually consisting of the sum of a sequence of payoffs. And in fact, we were looking at discounted payoffs. So the value of this actually should be equal to the immediate return that we get for that step plus the discounted total return if we start from the next step. So we get G of pi T plus 1. That will be, if you recall this definition, so that will be the weight of the discounted total sum of the segment of the episode starting at time T plus 1. right? And assuming that we're following the strategy pi. So we get this reward starting from the next stage, but of course we need to discount it by gamma, and then we plus the immediate reward of this current term, right? So this sum is exactly the same as this value. So essentially this is also what we want to approximate as using the MC's method, right? But if you think about this g, right, because we were eventually wanted to approximate g using the function q, so you can think of this g as some, previous step evaluation that we have already made. Recall that if we adopt a paradigm of bootstrapping as in the dynamic programming, we are always, making evaluation, and we're making updates to the evaluation. So we iteratively do that. At every stage of the run, we're going to have certain evaluation for every state and every action. So we maintain this Q function. And this means that this g t plus 1 pi, we can actually rewrite it. Instead of writing it as the exact payoff, the exact total return for the player, we replace it by the current estimated return that starts at state st plus 1, and suppose that the agent would apply the next action as a of t plus 1, right? So you can see that this is an estimate to this value. But what we can do is we can replace this using this whole thing. So we still have the immediate payoff of this stage, and then we plus the discounted expected return starting from st plus 1, assuming the agent adopts at plus 1 and follows the strategy pi afterwards. So we're using this to estimate the expected return. So in fact, we are using the current estimated return to evaluate the estimated return. That's bootstrapping, right? We're using itself to update it. But because we're doing this iteratively, according to the paradigm of dynamic programming, when it converges, it will actually converge to the correct value, namely the actual expectation of the return of the player. Right, so this is the overall idea of temporal difference learning, right? You can see the nice thing about the goal here in the last expression as compared to the target of Monte Carlo method is that in Monte Carlo method, we would actually need to wait to the end of the episode in order to estimate the current g pi t, because g pi t is defined on the suffix of a episode. This means that this can only be reviewed after the entire episode is finished. However, in the temporal difference case, the thing that we need is not g, right? We don't need to use gt pi to update our q. What we need is just the current value of the q defined on the next state and the next action, and then the immediate reward of this stage. That's it. So this basically means that the update could happen after simply we perform one step within the episode. We don't need to wait for the episode to finish. And that's exactly what we do for the temporal difference learning, right? Again, let's look at the comparison between MC and TD. For MC, we will need to obtain from a number of episodes the return value for all of these episodes. These are what's given to us by the experience that we generate. And then we compute the average of these values, and then we set that as the Q value. All right, so that's the high level sort of description for MC. We can in the last lecture when I illustrate those pseudocodes, I actually said we're taking average at each iteration. But in fact, we can change the implementation to an incremental implementation, just like for the k-armed bandit problem. We can rewrite this update rule, so the new Q value, like what I said, will be equal to the sum of all of the returns after we got t plus 1 samples, which visits SA, and then we get all of these returns, and then we divide by the number of times we have visited SA, right? So that's essentially if you recall, the on policy method for Monte Carlo method. That's what we did. But we can rearrange this to say that, well, actually this will be equal to, if you recall that if you just take the first t g value, so if you take the first t terms within this expression and divide it by t, not instead of t plus 1, then we actually get the previous estimate, which is QSA. Right? So if we rearrange this, we can actually rearrange it to the form of QSA plus 1 over t plus 1, which is a rather small value, multiply with GT plus 1 minus QSA. Right? But what is this? Well, if you think about it, we are trying to update our evaluation function, and the new estimation will be equal to the old estimation plus some small step size, and multiply with the difference between the current return, so the immediate return for this particular episode, for the next episode, minus the old estimate. Right? Isn't this familiar? Right? We can in fact rewrite it in this way, where Q prime SA is equal to the previous stage Q SA plus a small step size alpha, and in this case alpha will be 1 over t plus 1, and then times the error, and the error will be in fact the actual return that we get out of the next episode minus the previous estimation for S and A. Right. And of course, when you think about it, as t grows and grows, this part will get smaller and smaller. So in order for not this sort of update to diminish, eventually we can set alpha to be a small but a fixed constant. Right. So in fact, this is sort of the learning rule that we can apply if we were using Monte Carlo evaluation. Right. So this is still Monte Carlo. How can we define the corresponding temporal difference evaluation method? Well, we can actually adopt a very similar formation, because remember, the goal for Monte Carlo method is to estimate the the expected GT, and then we're actually using the true GT to update the Q value. But now our goal for temporal difference is to estimate this sum. Right. So instead of having GT, we can just use the same update rule, but replace the GT by this whole sum. And this is exactly what we do. Suppose Q is some sort of evaluation that we already have. Right. This is after processing previous experiences, we have got certain estimation Q function. And now, suppose I run another episode, but I do not finish the episode, but instead, suppose at certain step in the next episode, I visited SA. Right? When I visited SA, I got this reward, which is R prime, and then the transition would take me to a new state S prime, and then suppose at that new state, according to the current strategy, I will perform another action, namely A prime. So I actually got this 5-tuple SAR prime, S prime, and A prime. SARSA, SARSA. Okay? So we've got that step in the current episode, and where we visit this pair S and A, and now instead of waiting for the episode to end, we can directly update our Q value for SA. And how can we do that? We take the previous SA, and then again we plus with the step size alpha and multiply within the bracket. Instead of GT plus 1, we use this evaluation, because we know that after this step, we get an immediate payoff of R prime. And then we can just have a discounted sort of expected reward. So we take gamma, which is the discount factor, multiply with the previous estimate, but for the next state given the next action. So for Q of S prime, A prime, right? So that takes the place of GT plus 1. The benefit of that is that right now we only finish one step in the episode. We did not reach the last step in the episode, right? So after this, of course, we will need to take away the current estimate for SA, right? So this is the sort of the existing Q, and then we update the existing Q using this rule, right? And that will be the new value for Q of SA, right? You can see that essentially the TD evaluation still follows very much the same pattern as MC evaluation. The only difference is that we're not waiting for the episode to stop, but we are updating it on the fly as each step of the episode takes place, right? And each step can be represented. So all the information that we need is in fact this 5-tuple SARSA, and that's exactly the sort of algorithm that we will introduce, right? Just to summarize what I've just said, we were trying to solve the strategy estimation problem, the strategy evaluation problem. The input would be a strategy. It could be a pure behavioral strategy, and the output would be our estimation for the Q value. That would be the expected return to the agent given the state and given the action of the agent. Initializing this Q value, we get everything just could be 0. And then we go into several iterations. In fact, these iterations would be corresponding to episodes, right? And what we do is we initialize a state, and then we generate an action that's derived from pi from that state, and then we repeat for every step of the episode. Right? So while the episode is not finished, what we do is we take the action, observe the reward that we get, and look at the next state as indicated by the environment. So we're able to observe that. And then we obtain the next action, A prime, right, which is derived from the strategy pi. So we got everything that we need. We have the current state, we have the current action, we have the reward for this step, and then we have the next state, we have the next action. And then we can just apply directly this rule that I've just said earlier, QSA plus alpha times this value, so R plus gamma Q S prime A prime minus QSA. And then after that, I can update my S to be the new state and my action to be the new action. And I finish this step. And then I do this for every step. Right? So this will allow me to dynamically update all the SAs that I have visited during this episode, right? So after this, I finish this episode and I start another episode. So I repeat this until sort of at the moment where I want to stop, or this could be, a stabilizing moment, and then I return my Q value, right? And one can actually prove, although I'm not going to do that here, is that for any fixed policy pi, TD strategy evaluation converges to the target value in expectation. Right? And notice also that in the literature, this green difference here is also called a TD error, right? Because it's an error that we can derive using the current estimates, right? So basically, the immediate rewards plus the discounted version of the estimate minus the existing estimate, that's called the TD error. So that's the strategy evaluation algorithm using temporal difference learning. Now let's illustrate the idea using the next examples. Consider we have a random walk, and this is a random walk on a path. So essentially we've got this MDP that consists of a number of states, but they are linked in the sort of list fashion, where we have A is linked to B, B is linked to C, C is linked to D, D is linked to E, and the link is a two-way link. And there are two endpoints. One is to the left of A, the other is to the right of E, and that's only one directional, right? So once you reach these two states, you end the task. But on the left, before A, this box here, there's no reward. So basically, you get a reward of 0. On the right, if you go to the right of E, then you actually pick up this gold coin. So you get a 1 reward. All the other transitions have no reward attached to it, so it's all 0. And also, we're looking at the strategy, which is a random walk. So this means that the probability of moving left to right is a half, right? So that's that have equal probability from happening. And if you evaluate the probability for reaching the gold coin, right? For reaching the gold coin, you will be able to derive essentially a ground truth value for each state, because now we are not the agent, right? We are just looking like a god. We know exactly what the MDP is, so we can actually quite easily evaluate the expected return at each state, and this will give us 1/6, 2/6, 3/6, 4/6, and 5/6. So of course, if you're at E, you're more likely to get the reward, but if you're at D, you can you're less likely, but you're sort of the probability of getting the reward is 4/6, or the expectation of the return for you adopting a random walk will be 4/6, right? So this is the sort of the table that is ground truth, and we want to evaluate it. But now suppose the agent is deployed in this domain, and the agent is not aware of the situation, right? The agent just pick up a random walk as a strategy, and it tries to generate experiences on this domain, and in order to learn about the expected return at each state, right? So assume that we use the method of temporal difference learning, and then we fix alpha, which is the learning rate, or the step size, which is 0.1, and then we repeat a number of episodes. So you can see that at the very beginning, when we have 0 episode, the initial strategy that the agent pick is completely random. So it's at 0.5 at every so it's at 0.5 at every state, right? The horizontal line indicate the different states of the model, and then iteratively acquires more and more experiences. And using TD learning, you can see that the curve gets closer and closer to the true value, which is indicated by the blue line, right? If we compare TD learning with MC learning, so we actually do this experiment where you can see that the darker line correspond to MC, and the gray line correspond to temporal difference learning, and the vertical axis indicates the empirical error, right, of the learning process. You can see that TD learning results in much lower error from MC learning. So in fact, regardless of the value of alpha that we pick, we always see a faster convergence to the correct estimate, right? In fact, after only 25 episodes, MC has a much higher error than TD. Of course, eventually MC would catch up with TD, but it's just getting at a very slow and a much slower speed from TD, because in TD we have the capability of dynamically updating our evaluation every step as we go. So that's the illustration and comparison between TD and MC. Now we go on to discuss the optimal control problem, because that's eventually what we want to solve. And again, just like in the MC case, there are two versions of the problem. There's the on-policy version and there's the off-policy version. Right? But for the on-policy version, it's very straightforward. Essentially, it's very similar to the on-policy Monte Carlo. The only difference is that we are updating Q dynamically for every step of the way during an episode, so without the termination of the episode. And everything else looks very similar. Right? So what we do is we initialize a Q value, just like in the strategy evaluation. We initialize the Q value to be 0 for every state and action, and then we start with some sort of randomized initial policy. Right? This could be a policy that I'm just arbitrarily set, and then I repeat for a number of episodes. Right? And with every episode, what we do is we take some starting state, and then according to the current strategy, I take an action. Recall that this is on policy, right? So the on policy means that the experience that we use for training is exactly derived from the policy that we are currently optimizing. And so we just get this one strategy pi that we use to derive our experience. So we just using this current strategy, we get this action. And notice that just like in any sort of reinforcement learning algorithm, we will still need to take care of the exploration and exploitation dilemma, right? So obviously, in order to optimize our action, we will need to choose one that, from the current estimation, is the best action. Right? We'll choose that action. But because of the need for exploration, in order to really find out the true optimal action, we will need to be able to balance exploration with exploitation. And the most convenient way to do that is through epsilon greedy. Right? So anywhere when we want to find a new action, instead of just follow the greedy choice, we perform epsilon greedy exploration. So there's a percentage of time that we can just randomly choose another action. So this will guarantee that the action that we choose from any state, this means that every action is possible with a certain non-zero probability. Right? And then we go into this while loop. And in the while loop, we iterate over each step of the episode. While the episode is not finished, we will take an action, and we'll take this action A. So basically, we'll perform this action, and then the environment will give us the reward, and will tell us the next state. Right? And after we completed this action, then we look at pi, and then we say, okay, now I'm going to follow pi. So starting from the next state, I generate another action, namely A prime. Right? Again, using epsilon greedy explore. Right? So now I've got everything that I need. I have the current state. I have the action that I just performed. I got the reward, and I know the next state, and I also get the next action A prime. So what do I get? I get S, A, R, S prime, and A prime. S, A, R, S, A. Right? So I actually get all of these things, and I use that to update my Q value. Right? So again, this is the same as the strategy evaluation. And after that, what do I do? Well, I still need to improve my strategy. I can improve my strategy based on the Q value that I get. So basically, for this state S, I'll just need to choose the action which gives me the highest Q value. Right? And then in the next iteration, I'll reset my A to the next action A prime and the state S to the next state S prime. And this is repeated until the episode is finished. And once it's finished, you see that the Q value has been updated for every pair of SA that we have visited during this episode. And we then start another episode in this way. We can repeat this indefinitely until we feel like stopping, right? So like termination or whatever. And then we return the strategy that we eventually get, right? This will be SARSA, right? Just like the strategy evaluation algorithm, so this TD on-policy TD control will guarantee convergence to an optimal strategy pi, given that all the state action pair are visited infinitely many times, and the strategy converges in the limit to the greedy strategy.
Notice that because of the exploration-exploitation dilemma, if we fix the value of epsilon and we adopt this epsilon greedy exploration in the policy that we're trying to optimize, we would never be able to guarantee that the strategy converges in the limit to the greedy strategy, right? So in that case, this guarantee fails, and it will only guarantee that we will have an optimal strategy that is optimal among the epsilon soft strategies. So in order to arrive at the optimal strategy here, we need to implement some sort of greedy some sort of exploration that do not use a fixed epsilon when we apply epsilon greedy exploration. So for example, we can have these greedy exploration where we gradually decrease the value of epsilon, and in this way the strategy converges to the greedy strategy, and then we can guarantee optimality, right? So, in fact, this dependence on the value of epsilon being diminishing could be eliminated if we do not use an on-policy control algorithm. So there's a need to design an off-policy TD control algorithm, which we will present next. To illustrate the effect of SARSA learning algorithm, we again look at a very simple example. We look at gridworld. So we have this grid on the screen, and we have seen this location which is marked by S. This is the starting location, and then there's another location G, which is a goal location. And so we want to get from S to G, but the tricky thing is that at every position on the grid, we are faced with a wind. And the wind will have different strength across the different columns of the grid. And the strength of the wind are indicated below the grid, but just below every column. Right? You can see an integer number in the range of 0, 1, 2. And that's a number indicating that if we are making any move at that column, then regardless of the direction, will be automatically shifted upwards by a number of steps, which is indicated below the column. Right? So it's not obvious, and no longer obvious to reach. How can we reach from S to G? Because if we just walk right, we'll be pushed upwards by the wind, and we will not be able to reach G. Right? So we want to deploy this agent to find its way that goes from S to G in this scenario. You can see that again, we're having model-free scenario, even though we look at the model, but the agent does not know the model. Right? So you can see that why Monte Carlo method would not be a suitable learning algorithm for this case is that Monte Carlo algorithm would need to train on complete episodes. And here an episode will be the entire run that moves the agent from S to G. But because of this uncertainty within the domain, if the agent just randomly chooses its actions and aiming to complete an episode, it will actually not be quite easy for it to reach G. Right? Even though this is a very simple scenario, you can imagine easily if we modify the grid world, or if we modify the physical environment, then there are cases where if we just start learning and asking the agent to just perform random actions, in fact, the probability of completing the episode is almost zero. Right? And this means that if the agent cannot complete even a single episode, how can it learn using MC? Yeah, there's no way that it can learn. Right? So obviously, MC in this case would not be a very good choice for learning, right, for the agent in this scenario. On the other hand, temporal difference learning will be more suitable because we don't even need the agent to actually find the target location in order to update the value, right? Because we assume that every step that the agent makes within its exploration of the physical environment, this will cost the agent -1 reward, right? So with this information, as the agent is performing every action, we are able to update the Q value, and then learning takes place. So even though the agent may not be able to find the goal state, learning is always happening, and hopefully it will eventually improve itself and then find the goal. Right. So let's see how does the agent work if we apply SARSA algorithm, and then we're not counting the number of episodes right now because the episode may not complete. When it's completed, this means that the agent has already found the goal. So this is the number of times that the agent has actually reached the goal. And you can see that on the right hand side, we have a diagram which progresses as the agent is performing more and more time steps. Right? When it finds a goal, then it just restarts from the starting location. But we are counting the total number of steps that the agent have gone through and learn through the entire process. And what you can observe is that as the agent performs more and more steps, the curve have an upward trend. So it's not a linear curve, but it's moving upwards. What does this actually mean? So notice that the vertical axis indicate the number of episodes that the agent have completed. So this means that initially now you can actually see that in order for the agent to complete 50 episodes, so this means that the agent finding the goal position 50 times, it will roughly take the agent 5,000 moves, right? But to find 100, find the goal position for 100 times, it would roughly only take the agent another 1,500 moves. So you can see that this difference is quite drastic. This means that the agent actually improved its capability, right? Because it's now able to reach the goal state much, much faster than before, right? When it just started learning. And you can see that this trend increases to find the next 50 episodes. So to finish the next 50 episodes, so find the goal another 50 times, the agent essentially would need, I would say, roughly another 1,000 moves, right? So the actual ability of the agent is increasing. And then if you look at the outcome, after 8,000 steps, if you look at what the agent actually performed, it gradually stabilizes, and then from now on it will just
stay at the same rate. But then if you look at the strategy that it's adopting, it's actually finding quite an optimal way of going from S to G. It's going right for a bit until it reaches the position where there's a wind, and it just goes right all the way until it reaches the top of the location, and then it moves to the very end of the grid, and then goes down a bit, and then eventually it reaches go. Okay, so that's the result for performing SARSA. So we're doing this on policy training. And like what I said, for any form of reinforcement learning, in order to solve the optimal control problem, we have not only the on policy, then sometimes there's a need to learn optimal control using an off policy approach. Right. So how do we design an off policy temporal difference control? And this is actually regarded as one of the major step or one of the major advancement in the development of reinforcement learning, which is the invention of the first off-policy TD control algorithm. And the name of the algorithm is Q-learning, and that's probably the most famous reinforcement learning algorithm. Right. So we want to compare SARSA with Q-learning. So now let's think about what that is. In SARSA, what we did was we generate episode, and with each step in the episode, we look at the 5-tuple SARSA, which was generated using the target strategy pi. And then we use that to update our Q value. Right. In this way, the experience used to update the evaluation function is generated by the target strategy. Using Q-learning, on the other hand, we're not actually generating the experience used for learning using the target strategy anymore. In fact, the crucial difference is how we pick the next action. Right. In SARSA, the next action A star was derived using the target policy pi, but in Q-learning, the next action that we use for the learning experience was basically the greedy action according to the current Q table. Right, so we look at all of the Q values of actions starting from the next state as prime, and then we pick the one action A prime which gives us the maximum Q value. So essentially, this is sort of like when we are trying to learn, we are making a sort of a very brave or risky move. So this means that we are basically just choosing the one that looks to be the best, that's possible to give us the best outcome, and then we perform it. Right? You can see the difference between this and this is that this A star, this A prime, is generated by the target strategy, which is not necessarily the optimal action given the current Q value. Whereas in Q learning, we always choose that action which gives us the currently seen best Q value. That's the only difference between Q learning and SARSA. Right. So now we look at the actual procedure of Q learning, and I write it in a way that it's consistent, that it sort of mimic the procedure of SARSA. So there's a clear resemblance of Q learning with SARSA. Right. So what do? We do basically everything is the same before we go into the episode, and then the only difference occurs within the steps. So within each step of training, we keep an action which is derived. So this action A is derived from the current policy,
and also with epsilon greedy exploration. But and then we take this action, we can observe a reward, and then we can observe the next state S prime. So everything up to now is the same as the SARSA algorithm, the on-policy algorithm. But then when we choose the next action for training, we do not use the next action that's derived from the policy. Instead, we compute this A prime, which is the argmax among all of the actions A hat that give us the maximum Q value according to the current function Q, that give us the maximum Q value from the state S prime. Okay, so this is essentially the greedy action that's derived from the current strategy so this is essentially the greedy action that's derived from pi, that's starting from the state S prime. Okay, so this is not necessarily consistent with pi, but it's the greedy action from that state. And then we use this A prime to update our Q value, right? You can see that this is the only difference between SARSA, the on-policy temporal learning, and Q learning, is that when we are updating our Q value, we are updating it according to the greedy action, rather than just an action that's picked from pi. Right? And then again, we improve pi according to the current Q table, right? And then we set the new action to S prime, but then we define as a next action, which is an action that's derived from pi. Right? So you can see that there's a disparity between the action A prime that we use to update the Q value and the actual action that we use to make a move, right, to generate this episode. Right? And this is why it's called an off policy, because we're learning off the policy that that we actually follow to complete the task. So Q learning will guarantee convergence to an optimal strategy given that all the state action pairs are visited infinitely many times. Right? To illustrate the performance of Q learning, we use these classical example. Again, we're facing a grid world, but the tricky thing here is that if you look at the diagram, between the starting position S and the goal position G, the direct path, which is the most convenient path, actually walk alongside a cliff. So the cliff region is whenever the agent will step on it, it will fall off. It will create a negative 100 penalty to the agent, and then it will restart from the beginning S. Right. So this means that starting if the agent wants to really follow the path that supposedly will lead to the least number of steps, there is a chance of falling off the cliff and restart everything. So there's a chance to incur a very high penalty. On the other hand, there could be a more safer option, which is to go all the way up to the very top row and then walk right until reaching the very last column and then moving down to G. And that would be safest because it's having a very small chance of falling off the cliff. Right. So this example has been used by a lot of people to illustrate the difference between SARSA and Q learning. Recall that in SARSA, what we do is we simply just
follow the current strategy in terms of deriving the next action. And the update for the Q value will be just using the current action. So, and the action is, adopting a epsilon greedy exploration. So in fact, it explores quite a wide range of possible actions. However, for Q learning, the way that we update the Q value is through always choosing the action A, which gives us the highest Q value. Right. In this particular example, you can see that with every move, if the agent does not fall off the cliff, it gives a -1 payoff. So ideally, the agent would prefer, according to the Q table, those positions that are along the cliff tend to have a low Q value. Right. So in this sense, the agent, if it's adopting a Q learning by following the greedy action all the time, we would tend to give a high value for this positions that are beside the cliff, and then the agent is more likely to follow the optimal path, which is indicated by the blue line there. So starting from S, it goes all the way right to the goal state. On the other hand, the SARSA, being a sort of a more risk adverse type of agent, because when it evaluates it finds that there is a more chance to falling off the cliff, so that it will give a relatively low value for each of the positions along the cliff. So it will tend to stay safe and follow the green path to the goal state. Right? So that's the essential difference between these two. Of course, this is when setting an epsilon at a relatively high level. If epsilon is lower and lower, then we can see that SARSA move closer and closer to the actual Q learning. Right. But what we can guarantee is that, Q learning, of course, learns the optimal strategy. But the potential risk of Q learning is that it may occasionally fall off the cliff. So now we've finished discussion of these two temporal difference learning algorithms, namely we have Q learning and SARSA. And like what I said, Q learning is a very robust and well-known algorithm, has been applied to many situations. But now we want to go back to discussion of Markov games. Remember, originally we were talking about multi-agent systems, and Markov game, of course, extends MDP with the ability to have more than one agent functioning in the domain. But then instead of looking at optimal control of the agents, we're in fact looking at equilibria, where all the players are adopting their optimal control in response to their opponent. Reinforcement learning is in fact a very good learning paradigm that is suitable for the agents to find optimal control. Right, so basically arrive at equilibria in a Markov game. We focus on the simplest case where we have a two-player zero-sum game, right? And if you recall that situation, the MPE of the Markov game will actually force the min-max outcome. Basically, it corresponds to a strategy that maximizes the worst-case reward for both players. And now suppose that we face a situation where the agent is not fully aware of the payoff function and the transition, of course. We would like the agents to be able to learn the optimal control. Right? We define some variables, we call that V,
stands for the expected payoff to player I for any play that is consistent with a strategy pi starting from the state S. So this is our V pi IS. And then we can redefine Q function, but this time for 2 players instead of for single player. So the parameter takes state S and then 2 actions, A and O. A is the action of the protagonist player and O is the action of the opponent. So we define this function QI pi SAO as the expected payoff to player I for any play consisting with pi and starting from S with the players play action profiles A and O. Right. And now essentially we can apply temporal difference learning to evaluate this function QI pi iteratively. Right. So essentially the strategy evaluation problem can be solved in exactly the same way as for the single agent case. Right? We just need to think of for any sample step of the Markov game starting from S, given the action profile A1, A2, given the rewards to the players R1, R2, and given the next state S prime, we can we can update our Q value for S A1, A2, and this is the Q value with respect to player I, right? And that is equal to the previous evaluation at S A1, A2 plus the step size alpha multiplied with the reward to player I at this step, which is Ri, plus the discounted value, which is gamma times Vi pi at the state S prime. And what is this Vi pi S prime? That is defined as the max min value of the of the Q value for any action pairs A and O. Right. You can see that the difference here is that we're not just taking the Q value that we have, but rather we're taking the Q value, the prediction, which is the max min value, because we predict that the agent will follow the max min strategies at every step. Right. So this is the essentially applying Q learning, the same algorithm as Q learning for the 2-player zero-sum game. Right. And because of the fact that at each step of the update of the Q value, we take max min values or min max values. They're the same for zero-sum games, of course. Then we name the algorithm minimax Q learning. Right, the input would be a Markov game, a zero-sum, 2-player Markov game. And then the output will be the player I's strategy. Of course, assume that the player I is not aware of the payoff function, the transition function in the game. What we do is we initialize the Q value to be 0, and then we initialize the V function to be 0, and then we have some arbitrary random initial policy or initial strategy. And then we go into this loop, which is very much the same as Q learning, but the only difference is that whenever we want to update the Q value, we update it according to the formula that I gave you in the last slide. So we have Q of SAO plus the step size alpha times R, which is the current payoff, multiply with gamma times Vs prime, and then minus Q of SAO, right? And this Vs prime is then updated as the minimum value among all of the potential action of the opponent, and looking at the expected payoff to the current protagonist agent. Right, so this is the V value, and then when we choose the action of the agent to update the strategy, we take the max min action for the protagonist player. Yeah, so that's the only difference. And of course, potentially we could have mixed strategy when we decide the actions. So we're choosing, one of the mixed strategy, the best response which is the best response to the opponent's strategy. So that's almost the same as Q-learning. It's just minimax. So we adapt Q-learning as an algorithm, as a suitable reinforcement learning algorithm for the agents to learn how to play a zero-sum Markov game. So now the theorem says that under the assumption that all the action profiles are sampled infinitely many times, the Q value would converge in the minimax Q learning algorithm to the value of the game G in self-play. Right, the strategy pi converges to the Nash equilibrium strategy of the game also in self-play. Right, so this is a very good way that it describes not only what the equilibrium will be, right, what the MPE will be, but also it describes the dynamics of the agents, and starting from with no knowledge about the domain and no knowledge about the environment, and through this self-play, it iteratively learns about the environment and eventually find out the optimal strategy in response to each other, and that will be the MPE. Right, so that reviews this dynamics of the game. If we look at this example, we have the matching pennies game as the stage games of the Markov game. Right. So suppose that the agent which is playing against an unknown opponent using this game, the agent is just repeatedly playing this stage game of matching pennies, but of course the agent would not know at this stage the payoff function of the game. So what they do is they simply play using the minimax Q learning algorithm. He doesn't know the so the player would just adopt a minimax Q learning algorithm, and you can see that through the number of steps. So basically this indicates the number of stages that the players have gone through. They choose a sequence of actions, and then in response the player one will get a reward from that stage, and this reward is used to update the corresponding Q values. Right. And you can see also that, well, right now, because we're looking at just a repeated game, there's no change in the state. So when we represent the Q value, we don't need to actually represent the state of the Q value. So we just have the two actions by the player. So the actions could be either HH, HT, TH, or TT. And the Q value table is updated with every step in this way. Right. Notice also that after a while, so after T gets close to or more than 1,000 stages, there's actually a convergence of Q values to the Markov perfect equilibrium, and also there's a convergence of the strategies. Of course, the Markov the Markov perfect equilibrium of the game would be these players adopting a 0.5 mixture between the head and the tails. And in fact, this learning algorithm will lead the players to play that mixture strategy. And so that finished our introduction to the temporal difference learning algorithm. We started by looking at just a single agent case who is facing an unknown MDP, and then we've discussed how Monte Carlo algorithm, the Monte Carlo method, may not work in some situations, in particular those situations where the episode may not be completed in a reasonable amount of time. It's very difficult
for Monte Carlo algorithm to allow the agent to actually learn something useful. And to address this issue, we recall how humans learn and how humans update their estimations on the fly for every step of the way before the end of the episode. So we can actually implement this type of learning, which is temporal difference. We've introduced two temporal difference algorithm, which is the SARSA, that's what we call the on-policy algorithm, and Q-learning, which is the off-policy algorithm. The difference between these two are actually quite subtle, where SARSA essentially follows the strategy and then use that strategy as experience to update the Q value. Whereas in the Q learning, the algorithm follows the strategy, but then always use the greedy action as outcome to update the Q value instead of the actual strategy's outcome. And as a result, Q learning is a more sort of risk-prone type of algorithm. It aims to find the optimal strategy regardless of the possibility of incurring high costs, whereas for SARSA it's a more like a risk-averse version of Q learning, right? And then we extend temporal difference learning to the Markov games. And then we look at, instead of finding optimal control of a single agent, we're looking at the equilibrium where both players are playing in their optimal control in response to the other player. And we're looking at the zero-sum case where we adapt Q-learning to a mini-max Q-learning algorithm. And that solves the Markov game. So that finishes today's lecture. It also finishes our course. We have gone through a journey that starts by looking at some of the industry applications of multi-agent system and some of the algorithmic solutions. And this quickly leads to a realization that an economic paradigm will be very suitable for building up a theoretical foundation of multi-agent system. And then in order to do that, we start to look at the game theory. So our goal was to develop a sort of a systematic understanding of game theory, starting from the static games. We look at different solution concept of such games, and then we make a progress to dynamic games. So we look at these extensive form games where the agents are changing the dynamics of the game on the run. And we look at some simple dynamic games like multi-stage games, repeated games. We introduce Bayesian games, talk about games with incomplete information. And then eventually we look at Markov games, which is an extension of Markov decision process. And for Markov games and Markov decision process, if we assume that the environment is completely known, this means the transition and reward function are all visible to the agents, then we can just use a sort of like a dynamic programming style algorithm to obtain the optimal control for the agents or to compute the equilibrium of the agents. However, for the case when the agents themselves will not be fully aware of what's happening in the environment, there's a need for learning, in particular reinforcement learning. So we introduced Monte Carlo algorithm and temporal difference algorithm to do that. Right. So that finishes this semester, and I hope that all of you enjoyed the classes so far, and hopefully, in the future I will see you in some of the other courses.